Hello and welcome. Today we'll examine how to convert unstructured clinical knowledge and heterogeneous EHR data into fast, explainable, and workflow-native patient views. I'm Svetlana Makarova, and I am the AI Principal Technical Product Leader at Mayo Clinic. For those who are less familiar with Mayo, we're a multidisciplinary academic practice, education and research medical center with facilities located in Phoenix, Jacksonville, and Rochester, with the Mayo Clinic Health System locations across Iowa and Wisconsin. Today, I'll show you how AI can cut through the noise of transforming hours of manual data curation into minutes and surfacing only what matters at the point of care. We'll move through 4 sections. So first, the clinical data overload problem and why traditional solutions struggle. Second, an alternative curation approach we bring to the table using AI. Third, we'll talk about the technical architecture, the information retrieval, entity extraction, knowledge graph generation, and how we present the curated data. And finally, we'll cover the impact of this work with concrete steps for implementation. And with that, let's get started. So in healthcare encounters, clinicians face a data overload problem. A significant portion of these encounters, approximately 3 in 10, generates a clinical question. So whether it's preparing for a visit while speaking with the patient or reviewing the chart after the appointment, clinicians often consult multiple sources, such as open evidence, up-to-date, internal systems, clinical guidelines in their respective practices, to answer that clinical question. And a meaningful share of these clinical questions are answered with difficulty or not at all. And on average, they spend about an hour and a half per week on finding relevant data. In fact, research shows that physicians, especially in ambulatory settings, spent roughly 5 minutes per encounter curating data, which accounts for about a third of their total electronic health record use time. But what's interesting is what looks like an information problem is actually a data curation problem. So the right data is there, but it's scattered or fragmented across different systems, formats, and versions. And the cost is not only time, but it's cognitive load and delayed answers. So any approach that adds more data, more panels, new applications, or more toggles just amplifies that noise. So we have an opportunity to deliver a context-appropriate signal. Clinicians crave concise and actionable elements that reflect their specialty's mental model and the data that appears appropriate moment in the workflow. So in other words, not more data, but the right data on time and with a reason. And the last point I want to emphasize on the slide is that historically, clinical teams, especially at Mayo, want to tap into the organizational knowledge accumulated over 150 years at Mayo, which adds to this challenge and the opportunity. So how do we democratize this knowledge? Teams often start with handcrafted views. So a web of if-then statements per conditions and specialty. And there have been attempts in the past of doing this, even internally. In fact, there are even options to customize views in existing EHRs, but these require specialists, like IT requests, time. So this process is very brittle. And as you can imagine, guidelines change, interpretations differ by specialty, and getting agreement from multiple specialists on what information is required for each viewer is quite cumbersome. So as a result, roadmaps and delivery schedules of such viewers take a long time. With the build step, which you'll see in kind of that light blue, being fairly straightforward. So losers lose trust because data may be inconsistent and may not be personalized enough. So the lesson is clear. We need a composable, knowledge-driven system that evolves as practice evolves, and one that is explainable. So we flip the traditional approach by streamlining the requirements and build steps and spending majority of our time on validation and implementation feedback loops. And to demonstrate the scale of this problem, you must first realize that clinician needs are many to many. A single condition cuts across specialties, and each specialty emphasizes different data elements for different conditions. For example, cardiology view of diabetes differ from endocrinology. Psychiatry's views of lupus differs from rheumatology. Or take breast cancer condition that is usually treated by hematology oncology, thoracic surgery, and even plastic surgery, among others. And to take this further, a plastic surgery specialist, which is hopefully intuitive, sees different types of patients within their practice. And when we did a quick back of the envelope calculation, you see here 100 specialties approximately at Mayo raised to 139,000, which is the number of conditions and procedures in ICD-11. Hard coding every permutation is unscalable. So we need a shared knowledge that can be assembled into a specialty-aware view programmatically. And so our approach was guided by 5 questions. So think of this as a guide for understanding the context of the encounter situation to find what data is relevant and that is needed in that moment. So think of the who, which is the combined provider and patient context. So specialty, role, patient condition. The when is that moment in care. So is this an intake appointment? Is this a first-time consult? Is this a follow-up? Is this an acute event or a condition management appointment? The what is the candidate signals. So what labs, medications, symptoms, imaging findings? What are providers reviewing in that moment? Where does that source of truth lie or basically can be found? Is this clinical data in EHR systems? And why is this information relevant? So it's about understanding why it's relevant for that specific context. Sorry. And one of the other things that we had to consider was experience and how we plan to present this data. We needed a system that should infer context and automatically present a prioritized set of elements that a clinician would otherwise spend minutes assembling. Personalization should be additive rather than burdensome. So users can pin, they can hide, they can reorder data, but the default experience must already be proactive and explainable. So, and I demonstrate a few concepts that we've kind of played around with, but we do have a version of a system that we're currently, we already have in practice. And the pipeline stands on 3 pillars. So first, the information retrieval from sources clinicians already trust. So this is EHR data embedded knowledge. So we look at the historical data and we learn the patterns and marry those with trusted clinical guidelines. But more on this in a minute. Second, entity and relation extraction using LLMs and NLP tools to convert free concepts into relational structure. Third, knowledge graph generation so that we can compose views tuned to specific context and workflow. This graph then lets us ask relational questions that mirror clinical reasoning, and that lets us explain the answer. So let's focus on the first step, the information retrieval. We scope the information retrieval to the use case to reduce noise. So from the electronic health records, we pull minimal necessary information via FHIR. So orders, results, meds, problems, encounters. I can show that here because you could probably imagine any EHR interface would usually apply. From knowledge, we prioritize clinical guidelines, care process models, which is part of our internal knowledge systems, and other curated references. Again, the objective of the step is to retrieve what the relevant information is needed as part of that context or workflow. And the next step is entity extraction and standardization of clinical concepts. As you may have already guessed, guidelines and notes are long. They're varied and they're often ambiguous. We split them into atomic recommendations and constraints. Then we extract entities and relations using LLM-assisted pipelines that is schema first. Then units and abbreviations are harmonized and concepts are resolved to standards. So potassium is potassium everywhere, whether it's recorded as K+ or whether it's spelled out. And the way we handle entity extraction is best explained by a diagram published by IHIA 2019, an assembly line from raw text to structured facts. In our case, the raw text is clinical data and guidelines. We first chunk each document or information into meaningful units, sections, recommendations, and tables. We define a simple named entity recognition and relation extraction schema, and then we run NAR-RE to tag entities and link them. Next, we apply rule templates to normalize units, expand abbreviation, and capture if-then logic. And finally, we publish the knowledge as RDF, creating a queryable, explainable graph that downstream apps can use. And here's the practical step of flow of these steps to make it a bit more concrete, especially for those who are looking to learn and maybe implement it in your own respective organizations. We first ingest and chunk by structure, headings, tables, recommendation blocks. We define simple named entity recognition and relation extraction schema with fields you intend to use downstream. You would run extraction with constrained decoding and validate against the schema. Mine audit logs and usage patterns to learn which elements clinicians seek out first and which are of lesser importance. We then normalize the units, aliases, and then we map to SNOMED CT, LOINC, RX norms, and FHIR resources. We then build RDF with versioning so that you can travel from surfaced element back to the exact line and guideline version. You can then focus on building QA loops and focus on the delivery of these recommendations to the front end. Now, this is an example of a knowledge graph snippet. So the graph stores both facts and operators. Facts capture relationships and operators encode actions. Inference evaluates facts and operators against the current context to return an order set of elements with rationale. Again, this is a key point. It is prioritized. The key advantage of this approach is composability. So we have a single knowledge base that yields different views for different specialties without duplicating logic. Now you may wonder, do we generate this graph completely each time with new feedback or new information? And the answer is no. We use incremental knowledge graph generation, which allows us to merge new data with existing knowledge graph using iText to KG framework. And this is a demonstration example of what an output might look like. So consider a bipolar disorder example. The system surfaces the elements that are more likely to matter for this visit type, so this context, showing trajectories where trends carry meaning. Each item carries a rationale that links back to its source and version. The point is to place the most relevant information at the top with an explanation a click away. Related to the architecture, the system is layered and modular. Distillation turns clinical knowledge into machine-readable specifications. Normalization maps entities to standards. The graph and inference layer composes context-appropriate outputs. The presentation layer renders ordered elements with rationale in the workflow. And there's definitely more time we can spend digesting this, but I'd like to focus on one specific element of this architecture that may be the most useful to you, which is how we've optimized our feedback loops with automated prompt tuning. Now, we don't hand tune prompts, so there's no prompt engineering. We use principle-based model alignment loop that converts feedback into explicit rules and compiles them into prompts, which changes version and tests against objective criteria. This allows us the updates to become faster and safer, behavior stays consistent and explainable, and teams can scale improvements much more efficiently. And importantly, on the front end, we also implement explicit and implicit signals to provide additional feedback loops. The explicit signals are tagged with the exact element and action, which lets us know if additional data element is added, removed, or reprioritized. Implicit signals from analytics are also aggregated, and together they refine ranking and reveal gaps in the specifications. Importantly, one of our guiding principles is that personalization should be a byproduct of normal use, which is why we emphasize the importance of building these feedback loops in the first place. Now, for those who are interested in implementing something like this in your organizations, the implementation sequence is deliberate, and we'll briefly go through each one separately. But at a high level, you must first identify a high impact, measurable use case. Select techniques that are explainable and maintainable by your team. Embed the experience where work already happens. And then you establish feedback mechanisms upfront and make them easy to use. So you would start with stakeholder engagement to ask the questions. Which elements are hardest to retrieve and for what context? Map these workflows to using the 5 Ws framework that I shared in the earlier slides. You can score use cases by tangible business values, such as minutes saved, error reduction, cognitive load, feasibility, and then you'd validate data quality early, because there's no value in promising a view that depends on fields that no one will be using. Next, focus on selecting the core AI techniques for your use case. For distillation, keep schema simple and consistent. For NER and relation extraction, combine LLMs with deterministic checks. Choose ontologies you can operate and standardize on. For graph, pick a technology your team can index, secure, and reason over. The best graph is the one you can govern. Next, you want to meet clinicians where they are by deploying solutions natively into their workflows. You want to ensure Experian complements their workflows with customization options for the system to learn, so the feedback loops, and delivering hyper-personalized experiences, not disrupting it yet with another application. Performance also matters. You'd want to optimize for latency. And last but not least, and very importantly, ensure your organizational security and compliance standards are followed. Fourth, ship feedback early. Add a simple, obvious control to mark an item as missing, wrong, or helpful, and make sure each tag has an owner and a due date. Hold short, regular reviews with clinical and engineering leads to set priorities and track fixes. Watch real usage to see what's working and what isn't, and close the loop by telling users what's changed and why. So when curation works, the administrative load drops. The right data shows up in the workflow exactly when it's needed. The system updates quickly, new guidelines or feedback flow into the view without heavy lifts. And the real win isn't just speed, it's scale and personalization. Delivering the right data to the right person in the right context consistently. And with that, I want to thank you for this opportunity to present, and feel free to scan that QR code to connect with me on LinkedIn. Thank you.